today's talk is about machine learning-based solutions for modeling plasma-related processes. With the rapid growth in the volume of data produced by scientific community, machine learning has become a powerful tool for researchers to discern underlying patterns and extract meaningful insights from the vast data sets. Experiments and first principles calculations, they provide relatively accurate information, but both these approaches are typically time-consuming and they're not always feasible to carry out. In contrast, machine learning offers an expensive alternative to these methods, providing reasonably accurate estimations, but it is important to keep in mind that the accuracy of machine learning methods strictly depends on the volume and the quality of the input data. So machine learning has been previously implemented in diverse fields of science, including plasma physics and computational chemistry. For example, it has been used to predict particle properties in plasma spraying, to estimate plasma sputtering yields, to predict characteristics of plasma deposited films. And in computational chemistry, machine learning has been implemented to estimate reaction yields, to predict molecular structure of substances, and many compound properties like toxicity, bioactivity, solubility, melting points, atomization energies, etc. So the most widely used methods in the toolbox of machine learning are supervised machine learning algorithms. So a supervised machine learning algorithm learns relationships between input data or features and known responses to data or targets, so it can generate reasonable predictions for response to the new data. And typically, to build a machine learning model, the input data, which includes input features and target variable values, is divided into three sets: the training set, validation set, and test set. So the training set is used for learning the underlying patterns in the data. Validation set is used to assess the model's performance during the process of training, and it helps to fine-tune the model's parameters and to ensure that the model doesn't overfit. And test set is a part of data that remains entirely unseen by the model and is only used to test and to evaluate the model's performance, final model's performance. So Quantemol has previously implemented machine learning to estimate rate coefficients of heavy particle collisions, as Sebastian already mentioned, but I would like to give you a brief overview of this project. So typically chemistry sets for plasma modeling contain a large number of reactions, including heavy particle collisions, and many of those reactions might have missing kinetic data. So a reasonable way to get estimations for a large number of reactions, of kinetic data for a large number of reactions during a very short period of time is to use machine learning. And to build a machine learning model to predict kinetic rates of heavy particle collisions, we collected data from 4 different databases. So we collected rate coefficient values for around 1,500 reactions. And additionally, we collected as much as possible easily accessible data describing properties of individual species participating in the interactions, such as species molar masses, charges, standard enthalpies of formation, polarizabilities, dipole moment, etc. So we use this data to generate meaningful input features for our machine learning model. So, and to improve the accuracy of our model, we needed to perform our reaction data segmentation. So we split our reactions into 3 groups based on reactants charge combination, and we split those groups into another 2 groups based on the number of products. And finally, we split those groups in 2 groups, each of those groups in 2 groups based on the reaction endothermicity and exothermicity. So finally, we developed a separate algorithm for each of those segments. So now I'll show you how well the algorithm could predict the rate coefficients for different types of reactions. For example, the largest group in our test set, the largest group of reactions in our test set was a type of reactions in which one of the reactant is a cation and another is a neutral species. So our test set contains 146 exothermic reactions of this type and 175 endothermic reactions of this type. So the mean absolute error for the prediction of the logarithm of k was quite good. Sorry, for the exothermic reaction, the mean absolute error was 0.31, and for endothermic reactions, the error was slightly worse, 0.84. But if you look at the if you look at the distribution of the errors, you can see that for the vast majority of the reactions, the error for logarithm, the error for the rate constant itself is within one order of magnitude. However, in some isolated cases, the error was of 8 orders of magnitude, but so in these cases, the algorithm failed to correctly predict very low values of rate constants around minus 30, minus 20, and rate constants this low will not affect the solutions of plasma models as much as rate coefficients with higher values. So the group of reactions on which our model showed the lowest accuracy was the type of reactions in which both reactants are neutral species. Our test set contained 173 exothermic reactions and 274 endothermic reactions of this type. So the mean absolute error for both these types of reactions is very similar around 1.15. So, but we should keep in mind that this type of reactions is the least represented type of reactions in our test set. So the accuracy of predictions for rate coefficients for reactions of this type might be improved by if we increase the size of the test set. So yeah, as Sebastian mentioned already, our estimator for rate coefficients is deployed via in the form of web application as a part of QDB, and it can be accessed via this link. And so another project that we have started recently is related to developing a machine learning algorithm for prediction of electron impact ionization fragmentation patterns. So this information is often desirable to know. In plasma physics, it is often desirable to know this information. So in partial ionization cross-sections can be calculated using branching ratios for the production of fragments, which can be obtained from mass spectrometry data. But the problem is that for many compounds, experimental mass spectra are unavailable and it might be very expensive to conduct experiment or to use quantum chemistry methods to obtain mass spectra actually. And an alternative solution for this problem would be a data-driven approach in which we apply machine learning to known mass spectrometry data. So to implement this task of predicting mass spectra with machine learning, we collected mass spectrometry data for more than 7,000 compounds from NIST webbook. So they are quite relatively small compounds with molecular masses less than 300. And additionally, we collected SMILES data from the PubChem database. So SMILES is the way to encode the structural information of a molecule using a linear string of characters. So actually, using SMILES strings, we can extract numeric data describing molecular structure of compounds. More specifically, we can extract data that describes every atom and every bond in the molecule. For example, we can extract data describing the types of atoms, the valences of atoms, the number and types of atoms each atom is bonded to, the information regarding hybridization of atoms, the atom aromaticity, etc. Also, we can extract data characterizing all the bond types types of all bonds in the molecule, the chirality of bonds, the number of bonds in rings, the number of conjugated bonds, etc. And additionally, as input feature for machine learning model, we can use general molecular properties like molecular mass, the total number of atoms, and total number of bonds. So we can actually train a machine learning model on these numeric features to find the relationships between them and target mass spectrum. So for the purpose of predicting branching ratios, we decided to focus on fragments, only on fragments that result from breakages of single bonds only and contain only most abundant isotopes. So for example, in the case of 1-propanol, the target variable, we will include only the red peaks into the target variable. Yes, and each instance of mass spectra are vectors in which indices are mass to charge ratios, and values of each element are intensities from the mass spectra. So as a metric to estimate how well mass spectra was predicted by a machine learning model would be cosine similarity. For example, here y real is real intensity vector, y pret is predicted intensity vector, and m min and m max are minimum and maximum values of mass to charge ratio. So this cosine similarity, it can range between -1 and 1. And now I will show you, provide you examples of machine learning predictions from mass spectra with varying cosine similarities. Here, the orange spectra are the predicted spectra, the spectra predicted by our machine learning model, and the green peaks are parts of the real mass spectra. So, for example, in the case of 2-chloro-2-propene 1-ol, the cosine similarity between the predicted mass spectra and the real mass spectrum was 0.98. Sorry. So in this case, the predictions are quite accurate. You can see, the branching ratios that we calculate from these predictions will be also quite good. So another example of, for example, cosine similarity of 0.85 is etoxypropane. So here you can see that the algorithm overestimated this fragment with m over z at 73 that corresponds to the fragment arising from the breakage of from dissociation of one methyl group here. And an example of a cosine similarity of 0.71 would be of, for example, of 2-methylene butane nitrile here. So here we can see that the algorithm performed noticeably worse than in these two cases. So it greatly overestimated this peak at 20 m over z at 29, corresponding to CH3, CH2 plus. But overall, it's not that bad. So our best machine learning model so far is the extreme gradient boosting decision trees regressor. So here you can see the distribution of cosine similarities for around 1,300 mass spectra that we have in our test set. So for this model, for 80% of compounds in the test set, cosine similarity between predicted mass spectra and the real mass spectra is greater than 0.7. But this is so far, this is our preliminary model, and this hopefully it will be improved. So these are the conclusions for my talk, and thank you for your attention.